So this is the first video dealing with organic reactions. So I'm going to have two videos that kind of go through the main reactions, and then it'll have a couple others after that that point out a few individual or specific reactions. So combustion we'll deal with first. You've seen this before. Fuel plus oxygen yields carbon dioxide, water vapor, and of course heat, always exothermic. If the only two products are CO2 and water vapor, we say that combustion is complete or complete combustion, and no other products. Not so common, but we can have a look at it anyway. So here's an organic compound, butane. I'm sure you've heard of butane. Pretty commonly used as a lighter fluid because it combusts well. So good reaction to have a look at combustion with. So really all I want to look at is balancing combustion reactions. There's a format, an order of things when you want to balance. So typically we balance the carbons first. So I'm going to make that 4 CO2 to balance the 4 carbons in butane. You balance the waters or the hydrogen atoms next. And so if I make it 5 waters, I now have 10 and 10 on either side, and we balance oxygen last because we can do that with O2 alone. So I have 8 plus 5, 13, so 13 halves O2. So there's a balanced reaction for the combustion of butane, complete combustion of butane. Well, what if the supply of oxygen is limited? So we don't have as much oxygen. This is probably a little more common. If that's the case, we are going to generate a few other products. And again, you're probably familiar with this. I'm sure you've heard of this before. We can also produce carbon, and so you often see that in the form of smoke or soot. And we also produce carbon monoxide, which can be quite a dangerous product of incomplete combustion because it actually binds to your red blood cells if you inhale it, and irreversibly binds, therefore you can't bind oxygen. So it can be a problem. Anyways, when we go to balance this incomplete combustion reaction, let's just make note of that. It's incomplete combustion when we have carbon and or carbon monoxide present. So when you go to balance this, we still balance with our carbons first, but now I have 3 terms in which I can choose to try to balance the carbon. And you can try to balance with 3 different ratios or 1. I mean, really what it highlights is the myriad of different possibilities when combustion is incomplete. But I'm still going to balance with CO2, so I'm going to make it 2 CO2. So there's 2 carbons plus 1 is 4, so carbons are balanced. I balance hydrogens, that's still 5. Now I go to balance the oxygen, and I have 9 plus 5, or sorry, 4 plus 5 is 9, plus 1 is 10. So I make that 5 O2. And so one thing you notice now is the fuel to O2 ratio has gone down. And so that's evidence that there's less oxygen present. And when there's less oxygen present, you get other products. Now we can try that again by using a different carbon containing species to balance with. So I'm going to balance carbons using carbon monoxide, and so that's going to be 2 there. So 2 carbon monoxide plus carbon plus CO2, 4 carbons. Still have 5 waters. Now I look at the oxygen. I have 2 plus 5 is 7, 9. So that's going to be 9 halves O2. So again, you notice that fuel to O2 ratio is decreased. So incomplete combustion. We don't really get into combustion in too much more with the organic molecules, but nonetheless, these are good questions to consider from a stoichiometric point of view. That is, balanced chemical equation, products and reactants, how much do you produce if you start with and so and so. You know those types of questions. So that might be something that you get asked in the future. So keep in mind, you should be able to balance combustion reactions for hydrocarbons. Let's go on to another type of reaction. And so the first type of reaction I want to talk about is a reaction known as addition reaction. And it's pretty straightforward. Atoms are added to a double or triple bond. So we're looking at reactions involving alkenes and alkynes predominantly here in this example. The other thing is, recognition-wise, two compounds react to form one product. And so here is our initial organic reactant. So this is ethane. And so what's going to happen is one of those carbon-carbon bonds that is of the double bond is going to break. And when it does that, on each carbon you free up an electron, and those electrons can now form covalent bonds with components of this inorganic reactant. And so there they are. X and Y are basically added to my alkene, and there they are up here as part of the alkene, and I get an alkane. And so an alkene that undergoes an addition reaction produces an alkane. It's pretty straightforward. So let's look at a few examples. So here is my ethene. So ethene, 2-carbon alkene. I'm adding hydrogen. So pretty straightforward. What's going to happen there? There is a hydrogen added to one carbon. There's the hydrogen added to another carbon. And I still have only 2 hydrogens for my ethene. So ethene reacts with hydrogen to form ethane, a saturated hydrocarbon. So addition reactions basically saturate. Let's look at a reaction with but2-ine and hydrogen. So again, what's going to happen? Well, there's my triple bond, and electrons are made available on each of those carbons of the bond, and I get but2-ene. Okay, so the thing to recognize here is I have 1 mole of hydrogen. What if I had 2 moles of hydrogen? What do you think is going to happen if I have 2 moles of hydrogen? Well, obviously what's going to happen is I'm going to free up electrons, 2 electrons on each of those carbons, and so I'm going to bond 2 hydrogens. And so I get butane. So again, given the sufficient amounts of an inorganic reactant, I can saturate an alkyne. But there is a stoichiometric relationship there. So you have to keep that in mind. Finally, I can add water. So this is not something like a halogen or hydrogen. I'm now adding water, H2O, and we kind of look at water from an ionic sense here, but doesn't change what happens. So there's my double bond being broken to leave a single bond, and I'm going to add a hydroxyl group, and I'm going to add a hydrogen, and so I get ethanol. So the addition of water across the double bond gives you an alcohol. Another type of reaction, substitution reaction. So in this case, a hydrogen atom or a functional group is replaced or substituted by a different functional group. Okay, and there again, there is an electronegativity basis to this, but we're not going to get into that. But by recognition, 2 compounds react to form 2 products. But make note, the bonding of the carbon in the organic product does not change. We don't change the number of bonds or number of atoms bonded. So we're not forming double bonds or breaking double bonds. We have the same number of bonds off the carbon. So here's my general reaction. And again, so my X and my Y are basically going to swap. So the X was on the organic reactant, now it's part of the inorganic product. And the Y gets added or substituted onto the organic reactant and becomes part of the organic product. So again, it's a pretty straightforward type of reaction. So what's going to happen here if I have my ethane and fluorine. Well, everything's going to stay the same except I'm going to substitute a fluorine for a hydrogen. And so I get fluoroethane, and the inorganic product is hydrogen fluoride. What about substitution reaction with methane and chlorine? Well, again, we're going to produce chloromethane, so that's not very exciting. Why don't we make it 4 moles of chlorine? So what do you think is going to happen here? And just think about it. A substitution replaces a single, or substitutes a single hydrogen, for example, with a single chlorine. But if I have 4 moles of chlorine, what I'm going to produce at the end of it all is tetrachloromethane. Whoa. And I'm going to have 4 moles of hydrogen chloride. So again, don't forget stoichiometry. It still comes into play with substitution reactions. So here's an interesting one. So benzene, with its typical structure, typical Kekuli structure, shows this resonance of these double bonds. So a double bond separated, followed by single bond, double bond, that ordered fashion. And so when you look at that, you might think that this ends up being an addition reaction, and we would put on 2 bromines. So we'd end up with the dibromocyclohexadiene molecule. Well, I did also mention that benzene is not true double bonded. Those are 1.5 bonds. So benzene doesn't actually participate in addition reactions. So if you look at the aromatic structure, that doesn't get us sort of locked into thinking double bonds, it's a little easier to see what's actually going to happen. And so benzene actually participates in substitution reactions. So we're going to get bromobenzene and hydrogen bromide, because one of those hydrogens comes off the benzene ring. So just remember that benzene does not participate in addition reactions. It's substitution. So you want to make sure you remember that. All right. Last type of reaction I'm going to cover in this video, elimination reactions. And again, we've seen addition reactions. Well, elimination reactions are in essence the reverse of an addition reaction. Recognition, 1 reactant yields 2 products. So what we're doing here is actually forming a multiple bond. So here's my single reactant, and there's a carbon-carbon single bond, so it's an alkane, and at the end of the reaction I have a carbon-carbon double bond, so I formed a double bond. And in so forming a double bond, I produce a second reactant that are constituents that were originally bonded to the carbons. So there's an example. This is propane. And so elimination reaction, propane would yield propene and hydrogen gas. So a couple other examples. What if the organic reactant was chloroethane? Well, again, it's here that I'm going to form a double bond. And so there's my double bond. I'm left with 2 hydrogens, and I'm left with 2 hydrogens, and my second inorganic product is hydrogen chloride. And so the hydrogen chloride came from the chlorine and one of these hydrogens that is on carbon 2. What about an elimination reaction in propantuol? Well, again, Carbon 2 has the OH group, so that OH group is going to be gone. I'm going to form a multiple bond. So on carbon 1, I've taken off one of the hydrogens. Still have a single hydrogen left there, and I still have 3 hydrogens on carbon 3, and my other organic or my other inorganic product is water. So elimination reactions: addition, breaking a double bond, elimination, forming a double bond. And that concludes this video.